It's a great pleasure for me to introduce a collaborator and a friend and a colleague across the river from Pennsylvania, Professor Marissa Kozlowski.
Good morning. So I'm here to tell you the site for the next NOS. I'm going to be the organizer for the next National Organic Symposium. Before I do the big reveal, though, I'd like to bring your attention to the organization behind the NOS, and that's the Division of Organic Chemistry. If you want to learn more about us, you can go to our website. We're approximately 14,000 members, and this very large executive committee does an incredibly large amount of work on behalf of the members, organizing a large number of initiatives, including the NOS. And there are two individuals in particular that I'd like to acknowledge for this NOS. The first is our symposium chair, Scott Seaberth. He's done a fantastic job putting the symposium together, and I think he really deserves our thanks. So if you could join me and give him a warm round of applause. And one of the hidden people behind a lot of the things that the division does is Brian Myers, our webmaster. A thankless task. He keeps our website, which is very intricate and involved, up and running. I urge you to visit it. We have a lot of interesting information, including video interviews with prominent chemists. Soon we will have up the lectures from this National Organic Symposium, beginning with the Roger Adams Award lecture by Dave Evans. Pass the word on to your friends that any member of the division, and division membership only costs $15, will be able to have access to these lectures. And there are a number of other resources at the websites. Here he's collected all the tables of data, pKa tables, NMR tables, so I urge you to take a look at the website. It's a really great resource for organic chemists. And I'd also like you to join me in thanking Brian for all his incredibly hard work. Okay, so as you saw in a couple of posters, the NOS has a vaunted history. It has crisscrossed the country, beginning many, many years ago now. And if we look at the years and the locations, you'll see that a trend has emerged where on one year we'll have it on the west coast, west of the Mississippi, and on the other year, alternating year, we'll have it on the east coast or eastern Mississippi. So I can give you a hint straight away that it's going to be on the east coast. And after looking at a number of locations and considering things very quickly, we have decided on having it at the University of Maryland. And it'll be in 2015, July 28th or June 28th to July 2nd. The 2nd is a Thursday. Friday is going to be a day off. And July 4th is on Saturday. I'm joined by local organizers Lyle Isaacs and Michael Doyle. And the University of Maryland is located here in Maryland on the east coast of the United States. A little closer view, and you can see it's right here, about 30 minutes from Washington, D.C. and all the monuments and museums that one can find there. About an hour from Baltimore, and about 30 minutes from Annapolis and the Chesapeake Bay. So a lot of opportunities for vacation and entertainment there. The campus has an incredible amount to offer us. We will be having the lectures in a venue much like this one, their Performing Arts Center. Housing is located very close to the Performing Arts Center. There's a student union that's a little further away and that has a number of dining options. And then there'll be a banquet at the Armory. It's a beautiful campus. Here is the big M in the center of campus next to the student union. Their mascot is the terrapin, and it's really quite a beautiful campus. This is a snapshot of the Performing Arts Center and the hall we would be using for the lectures, so very similar to this one here, beautiful site. And outside in the hallways of the Performing Arts Center is where we would have the poster session over several levels. This is the site for the banquet, the Record Armory, a beautiful location. And as I said, there's a lot of advantages to being at the University of Maryland. It's close to a number of transportation options. There's a huge number of activities. Now, the only downside is I was alerted that it does get a little warm in Maryland at the end of June. But, and when I was touring the campus, I'd never seen this before, a university with an outdoor recreational pool. So I think we got all our bases covered there. So I hope to see you there at the NOS 2015 at the University of Maryland. We're looking forward to it. This will appear on the division website shortly, and we're going to start developing a list of speakers. I can only hope to match the strong lineup that Scott's put together here. All right, my next duty is to introduce our speaker, our last speaker for this event, Richmond Sarpong. He was born and raised in Ghana, and then he emigrated to the United States, where he attended Macalester College, and he worked in the labs of Rebecca Hoy for his bachelorate degree. Thereafter, he went to the East Coast, Princeton University, where he obtained his PhD with Martin Semmelhack. He made a trip to the West Coast then, working at Caltech with Brian Stoltz as a UNCF Pfizer postdoctoral fellow. And then directly thereafter, he began his career at Berkeley in 2004, where his research is focused on natural product-inspired transformations, particularly in the formation of 5- and 7-membered rings. Welcome, Richard.
Well, thank you very much, Marissa, for a wonderful introduction. And I also wanted to begin today by really thanking Scott and congratulating him on a really outstanding conference. But I have to take umbrage with you for making it such an outstanding conference from the standpoint of the speakers, because every talk has been wonderful. But what I've found at conferences is that there's often one talk that is not quite up to standard of the others. But since every talk so far has been wonderful, clearly I'm in trouble. But again, just a wonderful conference, and congratulations to you. And also to Professor Evans, who's our Roger Adams Award winner. Congratulations to Professor Evans. Unlike many of the speakers that were here this week, was not a student of Professor Evans's, but I've certainly studied his method. And one of the things that I've been impressed with from Professor Evans over the years is not only his many publications and all the wonderful work that his group has reported, but the fact that he's also an incredible teacher. And clearly a teacher that adheres to the Socratic method, where send students to the board to really learn by asking questions and having them answer questions and learn in that way. And this is something that I very much try to emulate in my own group. And so I wanted to begin today actually by really speaking to the students that are still here, especially the graduate students and the undergraduate and the graduate students that are here. And really present this talk really from the standpoint of thinking as a student would. And so my group is interested in complex molecule synthesis. We're especially drawn to alkaloids, which are natural products that contain nitrogens. And we really look to these molecules as a platform to identify important problems that one can address in chemical synthesis. And the solutions that we take to these problems come in the guise of the strategies that we choose to address these problems of complexity, as well as the tactics that we adopt to implement these strategies. And so we're interested in problem solving. And so clearly, I think for all of us here, problem solving is a trait that we value and we seek. But I would also argue that in addition to problem solving, the very best that emerge are also good at identifying the most important problems to solve. And this is certainly not easy. And so in my group, we look to do this by really focusing in an arena where problems will emerge. And in so doing, we will then be in a position to address problems that we consider important in the chemical synthesis arena. But I would also argue that in addition to being fodder for finding problems, complex alkaloids have also emerged clearly from their function standpoint as being important, especially when one thinks about the medicines that are currently on the market for small molecule medicines for treating various diseases. And so currently, about 50% of the drugs that are currently on the market have their basis, some genesis, in natural products. And here I've shown a small selection of the types of natural products that are in fact the basis for the medicines that are currently in the market. So clearly, there's a function value to preparing these types of molecules. And so our ability to make these in an efficient manner will certainly contribute to sustaining and improving life, which are things that Professor Nakamura told us about last night. And so this is what's really inspired my career at Berkeley since I started in 2004. And we've been interested in the synthesis of complex molecules. And on this slide, I show a small selection of the types of molecules that are of interest to my group. And so what I'll do today is really just present a series of case studies on how we've approached the synthesis of these types of molecules and the types of problems that has enabled us to address. And so there are two themes in our group, and I show these here pictorially. And so in one theme, we're interested in the synthesis of molecules that contain a 7-membered ring. And so I've highlighted these 7-membered rings here in these structures as shown. And so if I were to ask the undergraduates in the audience, especially following Professor Larry Scott's presentation, how one would put together a 6-membered ring, especially one that contains a double bond, I think without hesitation, each one of us would say, use the Diels-Alder reaction. But there isn't an analogy for that with 7-membered rings. And so clearly there's still work to do in terms of putting together molecules that contain 7-membered rings, especially those that are embedded in these types of structures. And so we thought there were opportunities for us to make contributions in that regard. The second aspect of our program has to do with thinking about how we can prepare alkaloid molecules that contain either a pyridine or the vestige of a pyridine. And clearly, because these are derived in principle from pyridines, it offers opportunities then to use a pyridine, and specifically a methoxypyridine, to address the synthesis of these types of molecules as shown here. Now, this is an old strategy that's well heeled and has been around for some time, and really was championed by some of my heroes in organic chemistry, like Ernie Wenkert and Bob Stevens, who was at UCLA for latter part of his career. But I will say, and I will contend, that what we bring to the table is not only this idea of using pyridines to build these molecules, but to marry that strategy with the idea of applying organotransition metal chemistry to enable us to effectively functionalize on the periphery of this pyridine or the vestige of the pyridines as we look to prepare these types of molecules. So we can bring the tools of modern methodology and marry that with this powerful idea of using pyridines to build alkaloids. And so I'll share a couple of case studies with you in that regard as well. So overall, one of the things that really brings all these projects together, obviously, is that we have to adopt strategies that enable us to build these types of molecules. And while we've heard a lot about methodology this week and also about strategy, I thought I'll take a minute and especially speak to the undergraduates and young graduate students in the audience to tell you about how we think about building molecules and what strategies we adopt. And so there are certain guidelines that we follow when we think about how to build complex structures, and these types of ideas have been around since the time of Hendrickson, Corey, and more recently Barron and others. But we're interested in building these molecules by thinking about the final target and working backwards in retrosynthetic analysis. And in so doing, we are looking to exploit the types of functional groups that are inherent to these targets and take advantage of those in building the natural products. We look for elements of symmetry that might exist in the target of interest and try to take advantage of those elements of symmetry as we look to prepare these molecules. We're mostly interested in natural products, and so we look to how nature puts these molecules together and then try to emulate nature's way of building these molecules in cases where this might be informative in arriving at an efficient synthesis of these molecules. And lastly, we're also interested in a lot of topologically complex molecules. And so this is somewhat of an esoteric idea, but we're very much interested in this idea of network analysis. And this is something that Professor Evans has actually championed in terms of thinking about consonant and dissonant disconnections for organic chemistry. But we're interested in thinking about ways in which we can disconnect molecules using this idea of network analysis. And so I'll try to point out throughout my talk these ideas as we go through the types of targets that my group has been looking to address. All right, and so I wanted to start today with this particular case study where we're interested in the synthesis of these types of molecules, casonidine and aconitine. And these are members of a larger family of diterpenoid alkaloids. And before I delve into our synthesis approaches to these molecules, I wanted to actually take a step back and talk about why we chose those particular molecules as targets. And so if one looks historically at alkaloids and alkaloid synthesis, one very quickly starts to have an appreciation for molecules such as quinine, morphine, strychnine, and so on, which have been studied intensely by people interested in chemical synthesis. So there are many syntheses of these molecules that exist, partly driven by the interesting structure, but also driven by the function of these types of targets. But I would argue that there are comparatively fewer synthetic approaches to these particular types of molecules shown here, the daphnophyllum type alkaloids and these diterpenoid alkaloids, which I think start to approach the limits of what we can do with the available tools for chemical synthesis. And I would argue that this is especially true in the context of these diterpenoid alkaloids if one considers the density of functional groups that is present on the carbon skeleton for these types of molecules. And so if we take a closer look at aconitine, and I'll do that, first of all, I should mention that in terms of synthetic contributions, I'm really drawn to the work of Carol Wiesner and David Jin, who were two of my heroes in synthesis that have really contributed to this area prior to some of the work that I'll tell you about today. And if you're really interested, you can read a lot about these molecules in this book by Tomas Hudlisky and Dorothy Reed. All right, so if we take a closer look at aconitine, one quickly starts to have an appreciation for the complexity of this particular target. And so here I've rendered in a two-dimensional format and here in a three-dimensional conformation. And very quickly one starts to appreciate that this is a molecule which is 6 rings, 3 of which are bridging. It has 15 contiguous stereocenters, 2 of which can be described as all-carbon quaternary. So clearly a molecule of almost impossible complexity, if you will. But I think that this is a molecule that we're now in a position to start to think about an effective synthesis for. Aconitine is famous for many reasons because it turns out that it's a very potent molecule. It's essentially a poison with a very low therapeutic index. But it's emerging recently in terms of the fact that it's a sodium channel activator, and sodium channel activation as well as the potassium voltage gated channel blocking is emerging as being important for neuronal molding and growth. And this is work that was done in the context of brevetoxin by people like Tom Murray. And so there clearly are opportunities to use these types of molecules and related compounds to start to understand the role of sodium and voltage gated ion channels and how neurons can be rewired. But from my standpoint, we first have to learn how to manipulate these types of molecules structurally before we can start to answer questions of function. And so most of what I'll tell you about today really has to do with structure and less so with function, which we think is the next step after we've learned how to build these types of molecules. All right, so if we look at this family of diterpenoid alkaloids, it turns out that there's quite some level of superficial variation in that family. But the philosophy in my group is that we look to address the synthesis of families of molecules and not just a single molecule, because if we can identify a common intermediate that would enable us to build not just one, but many molecules that overall could enable us to arrive at efficient access to a family of compounds. And so when we looked at the diterpenoid alkaloids, we recognized that these molecules were all related by a pattern of a 6-7-6 ring system, which is conserved throughout the whole family. And so I've highlighted here in red in all of these molecules. And so the idea was that if we could build this type of carbocyclic skeleton, then we could move ahead with the business of oxygenation and amination on this type of scaffold as we look to build this molecule in the laboratory. Now, given the fact that these are imposing targets, we decided to start with perhaps more modest targets. And so we decided to first learn how to manipulate these types of 6-7-6 ring systems in the context of molecules such as the ones shown here, which also contain that 6-7-6 ring system as highlighted here. And so the idea was to first prepare this, and so we wanted to ask the question before we embarked on a chemical laboratory synthesis of this 6-7-6 ring system, how nature might put together this type of structural motif. And so in order to learn about how nature builds 6-7-6 ring systems, I have to first tell you about the Stork-Eschenmoser hypothesis that was alluded to in earlier talks about how steroid scaffolds are built. So for example, how linosterol comes together. So that begins with squalene, which is first oxidized via epoxidation, and then an oxidase cyclase then affects now as cascade event, which stitches this together to afford this tetracycle. And then in a fantastic process, one has the series of migrations, which enables you then to arrive at linosterol. And so I think that this is just an unbelievable reaction for building these types of tetracycles. And so, as you would notice, this enables us to build 6-membered rings and a 5-membered ring, but how does a 7-membered ring arise? And it turns out that the 7-membered ring arises from a related process where the angular methyl group, which resides in the AB ring fusion, is oxidized and incorporated to arrive then at this 410 bicycle. Okay, and so this now makes the core of what is known as a cycloartane molecule. And so this is in fact how nature makes a lot of these 6-7-6 ring systems. Fantastic processes, but unfortunately, these are processes that are low yielding. And so in the instances where biomimetic processes are low yielding, I think that chemical synthesis can offer opportunities to address the synthesis of these molecules effectively. And so we decided to embark on a chemical synthesis way of putting this type of structure together. And so the question then is, how do we prepare these types of 6-7-6 ring systems? And we decided to adopt a strategy very much inspired, in my mind, by the Diels-Alder reaction. So we wanted to adopt a cycloaddition strategy to build 7-membered rings, but a cycloaddition strategy that would give us a 7-membered ring which is imbued with latent functional groups. So these double bonds I consider latent functionality, which we can then manipulate to either epoxidize, aminate at a later stage to incorporate the elements for the types of natural products that we're looking to build. And we're especially drawn to cycloisomerization strategies to build these types of tricyclic motifs. And so we thought that if we could begin with an alkynyl indene of the type shown here, we can perhaps manipulate this to the 6-7-6 ring system. And that would involve, in the productive sense, of activating the alkynyl group with a soft pi Lewis acid, which would then be lead to a vinyl cation, which would be engaged by this indene double bond. And I've rendered that here in this non-classical zwitterionic form. Now, if you're using a transition metal, that now has d orbitals that can interact with this positive charge, and so you can envision back bonding, which will lead to this metallocarbenoid, and that metallocarbenoid can now interact with the Walsh orbitals of the cyclopropane, which will lead then to this methylated cyclopropane intermediate that can suffer a demethylative strain release fragmentation to then afford this 6-7-6 ring system. Now, the beauty of a cycloisomerization in the ideal case is that you can take a starting material and simply in the presence of a catalyst, you can arrive at your product. And so this would represent then the sort of ideal atom economical process. And the other sort of advantage of these cycloisomerization processes is that you can traverse degenerate pathways that can also lead you to these 6-7-6 ring systems. However, the disadvantage of these cycloisomerization processes is that if you happen along a reaction coordinate that leads to a byproduct, this byproduct is an isomer of your product and also an isomer of your starting material. And often these isomers are very difficult to separate. And so the challenge in these types of reactions becomes one of selectivity. Can we achieve very high levels of selectivity in preparing this material and drive the reaction to a very high level of conversion? And so we have to choose the right conditions to enable us to carry out this type of process. And what we find is that using gallium trichloride, which admittedly is somewhat of an esoteric pyrolysis acid, that enables us to get very high yield, isolated yield, these types of cycloisomerization reactions to prepare these tricycles. And gallium trichloride was recognized about 12 years ago by Shantanu Murai to be very useful for these types of E9 cycloisomerization reactions, and its use in synthesis was really popularized by Professor Yamaguchi at Tohoku University, who really pointed us in that direction. And so with this in hand, we can now think about oxygenation chemistry to prepare natural products of the type shown here, which we've prepared. One can also begin with a nitrile group in the substrate, which is then parlayed into this bridging lactone, which is present here in isotexone and epiisotexone. We've furthermore shown that one can begin with these types of substrates, and in this particular case, we can use pyrolysis acids such as platinum chloride, which can affect the cycloisomerization to prepare this tetracycle, which we've advanced to this particular compound, which enables us now to then complete syntheses of molecules like cortistatin A. All right, so this is really the background for this idea of taking what is formally a 5+2 addition reaction to make 7-membered rings, and we've applied that to the synthesis of these types of molecules, and we thought that that then put us in position to now start to think about how one can prepare molecules of this type, which are in these diterpenoid alkaloid family. And so if, again, we revisit the slide on the diterpenoid alkaloids, we can actually look at this family and divide it into two types. The ones here in black and these ones highlighted in blue. And I want to start my discussion here with the ones in blue. And so these molecules that were in blue are actually further divided into two subtypes. The ones shown here, which are referred to as the hetidines. And these hetidines have this type of structure, and the ones shown here on the bottom, which are referred to as the hetacines. And the difference between the hetidines and the hetacines is that the hetacines contain an additional carbon-nitrogen bond. And so the idea of preparing the whole family and not just a single compound led us to choose the hetidines as a starting point, where we can then think about an oxidative carbon-nitrogen bond forming process to then stitch to form then the hetacene scaffold. And I'll point this reaction out, okay, because in the literature and historically, these are very difficult reactions to do. We can think about this as a CH functionalization, CH activation reaction. And really in the literature, there's only one way to do this type of process. All right, this is to use a reaction known as the Huffman-Leffler-Freytag reaction. And to date, there aren't any transition metal mediated processes that can enable you to do this type of reaction. And I would argue that this is one of the most important reactions that would in fact revolutionize the way that alkaloids can be synthesized were it to be invented. All right, and so our idea was to prepare the hetidine core. And we chose, as a way to illustrate our plan, navarine and cobusine, shown here in red, as the targets that we would initially focus on. And so these two molecules have never been prepared but that's not to say that there hasn't been synthetic work on these molecules. A related compound known as nominine has been synthesized by the groups of Jin, Shibunuma, and Moritake. Natsume have contributed wonderfully to this area, and so we really stood on the shoulders of giants when we first decided to tackle these types of molecules. And so when we thought about how we could put together these types of structures, we were also cognizant, obviously, of their function, which ultimately might lead us to learn something about how neurons are rewired, as I mentioned at the onset. All right, so in terms of a retrosynthetic analysis for how we wanted to put these molecules together, remember that we're interested in accessing not only the hetidines, but also the hetacines. We thought that these types of natural products could arise from simpler precursors. And in terms of where one starts a retrosynthetic disconnection, that's not very easy to think about in the context of these polycyclic ring systems. And so especially speaking to the undergraduates and some of the younger graduate students in the audience, we were drawn to this idea of network analysis. And what that basically says is that one has to identify a ring in this polycycle which has the most atoms that participate in bridging rings formations. And so if we can identify that ring, which is called the maximally bridging ring, and in this case it turns out to be the 7-membered ring, and we can disconnect about this ring back to a ring system which just has fused rings, that'll be a simplifying disconnection. Okay, and so here we can take away all the bridges and get back to fused ring system. That is simplifying. And ultimately, in a retrosynthesis, one wants to simplify. And so for us, we started to break bonds about the 7-membered ring, and so you can cleave the CN bond to get back to the hetidine ring system. And then we thought we could put together this 2-2-2 bicycle using an intramolecular cycloaddition reaction. Now, I wish I could take credit for this disconnection, but this is in fact a disconnection very much borrowed from the beautiful work of Professor David Jin and Kevin Pease, who had prepared a molecule called nominine using that 4+2 cycloaddition at a late stage. And then we thought that this type of diene could arise from methoxyarine of the type shown here via a reductive deoxidization in the forward sense. And then this particular structure would arise from this precursor, where in the forward sense we can think about a carbon-nitrogen bond formation. And then this then can be unraveled to the 6-7-6 ring systems that we built previously. All right, so I'll fast forward a little bit to tell you that here's a gin synthesis, a portion of the gin synthesis en route to nominine, where they take this precursor, simply treat that with pyrrolidine and methanol, that condenses to make the aminium ion, that then leads to a transposition of this double bond into conjugation, and the enamine form then undergoes a 4+2 cycloaddition to afford the 2-2 bicycle. It's a beautiful piece of work. And what Amy Hamling in our laboratory, and Amy's in the audience here today, what Amy had achieved in our laboratory was the synthesis of this molecule, which lacks this carbon-nitrogen bond, which is present in the gin and P system, and subjected this material to the same conditions that gin and Pease had used, in the hopes that, again, we would get this aminodiene and a cycloaddition to afford this material. And we had tried this reaction for many months, and we got trace, if any, of this product. And looking at this in more detail, we started to suspect that this hydrogen, this proton, was acidic by virtue of this form of the extended aminium ion. And that was actually important because if one epimerizes at this position, that can place the resulting aminodiene into proximity with the olefin group that then participates in the 4+2 addition. But in our particular case, the possibility existed that we might be unraveling this framework by virtue of having this carbamate, which is a reasonable leaving group. And that then ultimately will lead to non-specific decomposition. And so we had to revise our retrosynthesis to sort of remove this offending proton. All right, and so in our revised retrosynthesis, we thought that these molecules, so again arise from very similar precursors, but we would install a hydroxylation at this position, which will then block this epimerization and potential unraveling issue that we had. And we were especially drawn to the hydroxyl group because, as you will remember from our retrosynthesis, we were interested in the synthesis of molecules such as navarine as well, which do in fact possess this hydroxyl group. And so this would serve two purposes, enabling us to address the synthesis of these molecules that had to date not been synthesized, and at the same time prevent this deprotonation that might be problematic. And so the key, as opposed to our initial retrosynthesis, where we would prepare these types of cycloaddition precursors via a reductive dearomatization, here we would be looking at an oxidative dearomatization reaction. All right, so to walk you through a little bit of the synthesis, we can prepare these types of 6-7-6 ring systems. A diimide reduction removes this double bond, and then we can oxygenate at this position, which is benzylic and also allylic, using steric ammonium nitrate. And I have to mention that this is in fact one of the bottlenecks of the synthesis, where we can sometimes get capricious yields in that reaction. And so that's something that we still need to improve. So at this stage, we then carry out a removal of this double bond via reduction, where we're looking for phase selectivity between the phase bearing the cyano group or the methyl group. And so if you had asked me to bet on that reaction in terms of diastereoselectivity before Amy ran this reaction, I would have said that this would probably be poor in terms of the diastereoselectivity. But that proceeds actually with very high levels of diastereoselectivity to install the resulting hydrogen here and also at this position syn to that methyl group. All right, and so with that reduced material, we can then allylate by treating with sodium hydrogen and allyl bromide. That gives us a mixture of the C-allyl and the O-allyl compound. We can effect a Claisen rearrangement to then afford this material here. At that point, a reduction of the nitrile group and the carbonyl group affords an amino alcohol, and the amino group can be selectively converted to the carbamate, which then serves as a precursor for a cyclization reaction with thionyl chloride to afford this material. And so you can see that now we've prepared the left-hand portion of these molecules, and what remains then is to put together this 222 bicycle. We have unambiguous structural support by virtue of preparing this benzoyl derivative, this prepared nitrobenzoyl derivative, and obtaining X-ray quality crystals to support that structural assignment. And so with that material in hand, what we decided to do was to cleave this methyl group to unveil the phenol, and then subject that phenol to oxidative dearomatization conditions. And under those conditions, the Bach group is engaged, which serves to phase selectively deliver oxygenation from that phase. And that leads us then to this material. And with this material in hand, we can then effect dihydroxylation per iodide cleavage, so Johnson-Lemieux type reaction, which then leads us to this aldehyde. And this material is quite rigid, and that places this aldehyde in close proximity to this cyclohexane dienone. And so simply stirring this material with silica gel presumably leads to a high enolic content, which then affects then a Michael addition to afford this carbon-carbon bond, and then we can remove this double bond with rhodium and alumina and hydrogen, and then simply stirring this material with potassium carbonate and methanol then affects an aldol reaction to now afford the 222 bicycle. And so we were quite happy with this outcome. And again, we have unambiguous characterization for this material where it co-crystallizes with benzene. And so with that in hand, we thought we were in perfect position to address the synthesis of navarine and also of cobusine. But if you're discerning and you take a close look, you will notice that cobusine does not possess this hydroxylation, and navarine does not possess this hydroxylation. So regardless of which way we go here, we would have to effect a deoxygenation. Now, we're convinced that there's a natural product out there that has both hydroxyl groups. All right, so if you know that natural product, please point it out to us. All right, but what we really need to do then is really show the proof in the pudding that we can, in fact, convert this intermediate to one of these molecules. And we've recently done just that. And so we can begin with this material. For the purposes of preparing navarine, we have to remove this oxygenation, and we can do that by first converting to the xanthate, and then radical deoxygenation provides this material. Triflation using the Commons reagent affords this vinyl triflate, and then a Stille reaction installs the methylene hydroxy group, and then we can effect an esterification via the mesylate to afford this adduct, and then hydrolysis of the cyclic carbamate and oxidation of the secondary amine to the imine then affords navarine, which Amy Hamlin has recently completed in our laboratories. All right, so that starts to give you a sense for how we can apply this idea of a 5+2 cycle addition to the synthesis of 7-membered rings, and we're certainly applying those ideas to the synthesis of molecules in the diterpenoid alkaloid family. But I wanted to sort of point your attention in a little more detail at this family, and the fact that the strategy that I just outlined enables us to look at molecules of the type shown here, where we don't have oxygenation on the A ring, right? Whereas there are other molecules that have oxygenation on the A ring, and we thought that perhaps a better way to think about molecules like these, which have oxygenation on the A ring, would be to begin with a precursor of this type. Okay, a substituted hydrindenone, where you can see that hydrindenone mapped onto these molecules. And we like this idea of this hydrindenone because in our laboratory, we've worked very hard to prepare these types of materials in short order using a Diels-Alder reaction that gives good levels of diastereocontrol control in preparing the cycloadduct. And we've in fact utilized these types of cycloadducts to prepare molecules such as the fragmolin type limonoid framework, and we've also utilized these adducts to complete the synthesis of yohimbinoid alkaloids, alstovenin and venenatin, which was reported last year. And so in the context of molecules like aconitine, and so today I cannot deliver to you a total synthesis of aconitine, but I can at least tell you about where we are in terms of our progress toward aconitine-related molecules. We thought that the natural product could in principle arise from a precursor of this type, where we can effect oxygenation of this double bond at a late stage to install these vinyl hydroxyls. And this particular skeleton then would arise from this precursor, which is contains a vinyl cyclopropane. And this triggers, in my mind, this type of precursor. So it's a retron for what is referred to as a metapi photo cycle addition reaction. And Professor Seaberth would no doubt be familiar with this, having been a student with Paul Wender. But Paul Wender has been instrumental in really showing the synthetic community the power of this reaction. And so I'm very much inspired by the work that have been done in the Wender lab from that standpoint. And so we think that this would arise from a precursor of this type. And then this then would arise from these substituted hydrindenone compounds, which can be prepared from the Diels-Alder reaction. So I'll just give you a quick sense for where we are. Clearly, this meta-photocycle addition is the key step in this our ideas for how to put together these molecules. And so if we consider the aconitine case, we start to think that, in fact, this type of cycle addition idea could be applied not only to the synthesis of aconitine, but related molecules in this diterpenoid alkaloid family. And so, for example, if one looks at a molecule like aconazine, we start to appreciate that simply changing, for the most part, the arine partner would enable us to start to access other types of substitution patterns on the desired molecules. And not only that, but we can begin with related compounds, which instead of carrying out a meta photocycle addition, we can carry out 4+2 cycle addition chemistry to access completely different skeletons in this diterpenoid alkaloid family. And so in that sense, we think that we can arrive at a common intermediate somewhat related to this that would enable us to access all of these different structures. And so just to show you where we are, we can begin with these cycloadducts that we can access in large quantities. carry out vinyl triflate formation, cross-coupling with a cyano group to arrive at this material. We can now carry out conjugate additions of different substituted arenes, and that proceeds from the convex phase to afford these types of adducts. Here I just show it simply with a phenyl ring. With this material in hand, we can carry out a mild hydrolysis of the nitrile group using this really wonderful catalyst by Gaffar and Parkins. And that affords then the carboxamide. This then is subjected to oxidative Hoffman rearrangement conditions, which in the presence of methanol leads to the formation of this carbamate. And also in the same pot, we can remove the silyl group to afford this primary hydroxyl. The primary hydroxyl is then converted to the mesylate, and then an alkylation reaction with T-butoxide then affords this material, which has been unambiguously supported by the crystal structure that we've obtained. And so we believe that this really puts us in position to address the synthesis of not only this molecule aconazine, for which we are now on the doorstep of this precursor, but also ultimately of aconitine and related compounds like amandanine. All right, so this is one of the case studies that I wanted to share with you today, which really began with our interest truly in aconitine, but this is still a target toward which we're working. I wanted to now move on and tell you about some of the other chemistry that has really been inspired by this strategy that we adopted, which was this idea of a formal 5+2 cycloisomerization to arrive at the 6-7-6 ring system. Because when we looked in the literature and thought about how we could put together these types of precursors, what we quickly realized is that we were woefully inadequate in terms of thinking about cross-coupling reactions that would enable us, for example, to stitch together the acyclic portion here with this sort of substituted indene that would be required for the cross-coupling. And so that really led us very quickly to think about ways in which we could prepare substituted indene molecules. And so we've invented some methodology where we start from propylic acetates and we can now effect cycloisomerization to arrive at substituted indenes. One can begin with epoxy substrates and utilize these epoxides to ultimately arrive at these acyloxycyclopentanones. We can begin with aziridines and arrive at these unusual dihydropyridines. One can begin with pyridines and arrive at these indolazine compounds by virtue of what I consider as this type of intermediate. One can also begin with propylic alcohols, which are enantio enriched, essentially enantio pure. And again, by virtue of this type of an intermediate, which then undergoes a migration of the ethyl group to the ring fusion position, one can arrive at indolazinones. One can also begin with these types of substrates and arrive at these types of indolazines. Now, I move through this pretty quickly because the appreciation that I want you to take away from this is that we are now able to access these quite unusual heterocycles. And so they might be of interest to you, for example, from the standpoint of patent busting and looking at how you can replace an indole for Marco-4 with these indolazines. But we're interested in these from the standpoint of complex molecule synthesis. And so when we look at these particular molecules, we start to appreciate the vestige of these types of indolazines and indolazinones. And we've been interested in applying these types of methodologies to the synthesis of these molecules. And so, in fact, we've completed a 5-step synthesis of this molecule from very readily available precursors. And I wanted to share with you today a related 5-step synthesis of this compound called coquilidine, which begins with this iodoisoquinoline, which, in fact, we prepare using the Noshel chemistry. So the chemistry that Professor Noshel told us about this week, where we can effect deprotonation and iodination at this position. However, if we take this iodide and we carry out a halogen metal exchange and then quench with this Weinreb amide, we can arrive at this adduct. Treating that adduct with ethanol Grignard affords the adduct, which unfortunately proceeds with very poor levels of diastereoselectivity. But I should mention that when we started this particular project, it was unclear which of the diastereomers of coquilidine was a natural product. And so, in fact, in a sense, it served to enable us to get to both diastereomers. All right, so with this material in hand, what we've shown in our group is that we can simply treat these types of propyogenic alcohols simply with protic solvents like ethanol, and that affects a cycloisomerization to afford these two products starting from the two diastereomers of this material. Okay, and as it turns out, is this particular diastereomer here, which leads to coquilidine. And so we can simply take either one of these compounds and simply carry out an ionic reduction which removes these two double bonds to arrive at this material. And so after 4 steps, that's where we were. And what really remained was to stitch together this olefin group and this carbonyl group to arrive at this material. And so I should tell you that we looked at a bunch of different reactions. We looked at methylations and trying to carry out ring closing metathesis. We looked at methylations and trying to carry out relay ring closing metatheses. And all of these really were thwarted, I believe, by the steric encumbrance, which is makes this sort of a neopentyl site. Yeah? And ultimately what we found is that this chemistry works beautifully if you simply treat this material with the Schrock alkylidine, and that now carries out a carbonyl-ene metathesis reaction to arrive at coquilidine, which again is unambiguously supported by crystal structure. All right, and so this is the story that I wanted to tell you from the standpoint of our interest in preparing natural products which contain a 7-membered ring. And this has ultimately led us in many directions in terms of methodology development as well. In the remaining time that I have, I wanted to move on and tell you about our interest in using these pyridine derivatives to prepare natural products such as the ones that are highlighted here. And our interest in this area really began with this compound called lyconidine A. And lyconidine A is a member of a larger family of lycopodium alkaloids, and I show here a small subset of this family. And much like our interest in the diterpenoid alkaloids, we're interested in this family as a whole. And so we looked for patterns that were conserved in the whole family. And these would be patterns that would enable us to perhaps prepare a common intermediate that we could then parlay to other members of this family. And so we thought that this part in blue was conserved throughout this whole family. And so if we could prepare something approaching that part, we could then prepare the other molecules in this family. Now, lyconidine is shown here, and we're not the only people that have been interested in the synthesis of this molecule. We're very much learned a lot about this molecule from a first synthesis that appeared from the group of Professor Amos Smith at the University of Pennsylvania that really laid the groundwork for how I think everybody else has thought about putting these molecules together. Recently, Professor Fukuyama has had a beautiful synthesis of lyconidine A that has appeared as well. But as I mentioned, our interest is in the synthesis of a family of natural products, which includes lyconidine A. And so when we thought about this family, we thought that all of these molecules could arise from this type of precursor, which ultimately would again arise from this type of 6-7-6 ring system. All right, but given the time, I'll simply fast forward to tell you that we can, in fact, prepare this molecule. And what remained at a late stage was the fact that we had to stitch together this nitrogen and that carbon, right? This is the problem that I sort of mentioned at the very beginning, that if we can do this type of C-N bond formation from an sp3ch bond to an NN dialkyl group, it will really change the way in which we do alkaloid synthesis. And so this is the challenge that I'll throw out there to anybody. If you're able to solve this problem, I will forever be indebted to you. But in any case, we can prepare this molecule, and we needed to make this carbon-nitrogen bond. And if you look at this material, it's a rigid polycycle. And when one has these types of rigid polycycles, where the nitrogen is proximal to a methylene group of that type, the reaction that exists to do this type of functionalization is the Hofmann-Loeffler-Freytag reaction. All right, and so we're working on this in December of 2007, and the person working on this project was a postdoc by the name of Alakesh Pasai. So I'm from Ghana in West Africa, as Professor Kozlowski mentioned, and so this is December as the holidays. I bought a ticket, an expensive ticket, to go back to Africa to visit my parents. And Alakesh had also bought an expensive ticket. But he'd bought a ticket to go to Las Vegas to celebrate his impending completion of this natural product target, okay, because he was convinced that everything I'm going to tell you about now was going to work. All right, and so Alakesh ran off into the laboratory and came back telling me that he had this material, and I said, that's great. Let's simply chlorinate the nitrogen to afford this N-chloro compound. And he came back 2 hours later and told me that reaction worked beautifully, and he got excited about his trip. Because what remained was that we were going to take this material, treat it with a strong acid like trifluoroacetic acid, which will quaternize that nitrogen, and then we will irradiate this, which should lead to a homolysis of this N-chloro bond to afford an ammonium radical, which will abstract this hydrogen atom, which upon recombination with the chlorine atom will lead to a precursor to our desired carbon-nitrogen bond formation. And so Alakesh was visibly excited, run into the laboratory. He was gone for a day, he was gone for 2 days, and he finally emerged dejected, okay, because what he found is that we formed this bizarre aziridine and not our desired CN bond form product. And we believe that this aziridine arises from a Hofmann type elimination where we lose this chloride as a nucleofuge, which presumably might lead to an incipient nitrine, which aziridinates on this double bond to afford this material. So I went home to Africa to visit my parents anyway, and Alakesh had the ticket, so I guess he had to go to Vegas, all right? But he came back enthused, presumably because he won a lot of money. I still don't know, but he was very enthusiastic. He looked at other atom transfer reactions. We looked at this N-iodo compound, and that was spectacular in its failure. From the standpoint that we simply lose HI to form the imine. We got desperate, and so we looked at the N-nitrosa compound, really harkening back to the work of Barton on the nitride ester synthesis, and again, that also failed. We also looked at the N-sulfide, and again, that also failed in terms of transferring the sulfur group as a precursor to hydroxyl at that position. And so at this time, this is very much starting to seem like our Sisyphean effort, right? Where we're rolling that proverbial rock up to the top of the mountain only to have it cascade back down. And in fact, if you look really closely, it's sort of a resemblance between these two, okay? But this is what I love about complex molecule synthesis, because when you're stuck between a rock and a hard place, it really forces you to think outside the box. And so we were desperate. And so what we decided to do was to just step outside the box. And so when we looked at our precursor to this carbon-nitrogen bond formation, what we started to appreciate about this precursor was that it sort of looked like a glorified version of disopropylamine, right? A precursor to a lithium amide base. And so what would happen if we treated this with something like N-butyllithium, which would deprotonate to the secondary amine? Could we perhaps effect a deprotonation of this sort of benzylic position? Because after all, if one looks at the Bransma pKa scale and looks at the pKa's for secondary amine and THF versus what is really a special type of benzylic position, because it's picolinic, if you will, this is about 36 and that is 34. So it's not unreasonable that we can form a dianion, and perhaps if we take that dianion and we oxidize it, we would form a CN bond. I know it sounds crazy, but we were desperate, right? And so this is a situation where we want to take advantage of the inherent functional groups in this molecule to prepare our target. And so indeed, when Alakesh treats this with N-butyllithium, we know that the first equivalent forms the N-lithium compound, which at low temperature exists as a dimer. And this is in fact also true for LDA and THF at low temperature. And with the addition of another equivalent for N-butyllithium, he forms a deep orange solution, which we assumed to be a dianion, and simply treating that dianion with iodine now affects that CN bond formation in 95% yield. And this was great because we simply had to cleave the methyl group to arrive at a synthesis of liconidine A. So from a synthetic standpoint, this was extremely satisfying, right? But from the standpoint of an academician, it was very disturbing because we did not understand the nature of this dianion intermediate. And so we've looked at this in a little more detail. we can take this dianion and treat that with a small, hard electrophile like deuterium, and that leads to a stereo-specific introduction of the deuterium as shown here, which we can deconvolute using NOS techniques. And so we get a 72% deuterium incorporation, which means there's still 28% of protio. And so you can run what is a qualitative kinetic isotope experiment, right? And so if you take this material and you treat it with n-butyl lithium, what we find is that when we quench with water, protio water, we simply remove all the deuterium. And so that tells you that this substrate will rather dedeuterate than deprotonate, right? And so there's clearly something special about this position. And not about the deuterium, because if you quench with deuterium, you simply enrich and enhance this particular position. And so all of this was starting to tell us a little bit about the nature of this carbon-lithium bond in our mind. And this week we've heard a lot about bonding, and it turns out the carbon-lithium bond has been argued for a long time in terms of the nature of that type of bond. And so people like Andy Streitweiser in my department, Paul von Ruck-Schleier, Bob Gawley, Gideon Frankel, many have really looked at these types of bonding, and the belief is that these types of bonds are about 20% covalent and 80% electrostatic, right? But we think that there is some sense of the position of that lithium bond in that particular dianion. But remember that in our reaction, we do this with iodine, and iodine behaves differently from deuterium, so we needed to try to get a better sense for the nature of these dianions, and we've collaborated with Dave Collins' laboratory, and indeed the two lithiums that reside here are in distinct environments via lithium-6 NMR, looking at the nitrogen-15 isotopomer of this particular dianion. And so we have a pretty good sense, we think, of what this looks like. However, the chemistry with iodine is not necessarily the same as the chemistry with deuterium, because iodine is a much more diffuse polarizable electrophile. And so the question was whether, like deuterium, iodine is also introduced with retention. And so we tried very hard to isolate these types of intermediates, but we had very little success, because every time we try to isolate these iodides, we simply get the CN bond formed product, which we show here as a salt, the HCl salt, which we obtained crystals for. And so clearly this reaction of CN bond formation, if we were making this iodide, was very facile, and that started us thinking a lot about the nature of the iodine and how it's introduced, because that facility almost suggested that the iodine must be introduced with inversion and not with retention, which will better align the Ci sigma star with the approach in nucleophile. And so when we dug a little bit further into literature, we find that indeed there are instances where one can get an invertive addition of an electrophile in these types of reactions. And so people like Appelquist, the work of Peter Beek's laboratory and others have shown this to be the case. And so given the time, I won't dwell too much on this, but we could still not discount the possibility of an alpha elimination to form a carbene that could simply insert into the NH bond. And so that was always possible. And so we've looked at this in a little more detail, and I will save you the gory details, only to mention that using sulfur electrophiles, which are also diffuse and polarizable, we can in fact isolate this adduct where the sulfur is introduced with inversion. But with the caveat that this chemistry can also be single electron transfer chemistry, because when we use oxidants like TEMPO, we also obtain these products, which is consistent with reports from Newcomb and Ashby and others. All right, so this story on lyconidin taught us a number of things. One of the things that it taught us is that, first of all, if one can carry out what is this formal dehydrogenation reaction, that can enable you to stitch together lots of different caged alkaloid molecules. And it also taught us that these methoxyarenes were really an excellent surrogate for pyridone. And in particular, these methoxyarenes had significantly reduced basicity at the nitrogen compared to pyridines. And so this is something I wanted to talk about in a little more detail, because it turns out this has become very important to us in the context of alkaloid syntheses. And so if one looks at pyridine, and we look at the pKa for pyridine, and look at the conjugate acid, we find that's 5.23. If one looks at picoline, which has this methyl group, which is inductively donating, it's not surprising that this conjugate acid has a pKa of 6, which is clearly tells you that this is more basic than the pyridine. However, if one looks at methoxypyridine, the corresponding conjugate acid has a pKa of 3.06. So that tells us that the methoxy group actually mitigates the basicity of that pyridine, which seems a little bit counterintuitive, because from a resonance argument standpoint, we would say that this methoxy group would stabilize the positive charge. But it turns out that actually that inductive effect is more pronounced as compared to that resonance effect. And if one looks at the methoxymethylpyridine, that sort of splits the difference. And so these are thermodynamic arguments, but the arguments go a little bit further in the sense that if one considers this methoxymethylpyridine and this particular conformer of the methoxy group, that methyl group actually blocks the approach to the lone pair on the nitrogen, okay, which is shown here in this electrostatic potential map, whereas for pyridine, that is very much open. And so we think that there's actually a kinetic encumbrance to the approach to that nitrogen lone pair as well, which contributes to how well behaved these methoxypyridines are. And so you might be asking the question, wait a minute, this is a single bond, this free rotation, why are you suggesting that that's important? And so, in fact, you can look at conformational pictures for these methoxy picolines, and one finds that indeed this particular conformer is preferred. This has been shown in our laboratory and also in this paper from the Corey laboratory. And Professor Diedrich mentioned cases of where these sort of conformations become important as well. And we believe that this particular conformer is preferred because it minimizes dipole interactions between that lone pair and the lone pairs on that oxygen. All right, so we've taken advantage of this mitigated basicity of these methoxyarenes in a number of syntheses from our laboratory. Here I show one example from our work on lycopyramine R, where we can now utilize these methoxypicolines to prepare this molecule in 14 steps. I'll also point you to this paper from our laboratory by Rebecca Murphy, who's here in the audience, where we've applied the same idea to the synthesis of megelanine-type alkaloid molecules. We've furthermore applied these methoxypyridines to the synthesis of this natural product, alkaloid GB13. And what I wanted to finish up with here today is to tell you about how these methoxypyridines have become important to us in how we think about the synthesis of molecules like this one, complanidin B. But to tell you the story of complanidin B, I actually have to begin with complanidin A, which is a related molecule. And complanidin A is shown here. These are molecules that are found in the lycopodium alkaloid family. The most famous member of this family is a compound known as huperzine. And huperzine is in fact used to treat memory loss. It inhibits acetylcholinesterase, and that treats the symptoms of cognitive decline. And so there's interest in these molecules. But some of these emergent members, like complanidin, also induces the production of nerve growth factor. And so people actually believe that that could be important in how we think about reversing the effects of cognitive decline. And so if one looks at this molecule, it's a little bit hard to appreciate, but this is actually a molecule which consists of two halves. All right, and so the portion here on the left is actually the same as the portion here on the right. I've just rendered this from two different perspectives. But clearly, as a card-carrying synthetic organic chemist, and after everything I told you about in the introduction, we were drawn to the idea of taking advantage of symmetry in terms of how we would prepare this type of molecule, right? And so if we could cut this in half, then we only had to really process half the material and do half the work, and then stitch this together at the very end to put together this molecule. And so that's the way in which we went about putting together complanidin A. We thought that this molecule could arise from the two halves, but there was a complication in the sense that this was a dimer which was not truly symmetrical. It's a symmetrical dimer, in the sense that the 3 position of one of the pyridines was bound to the 2 position of the other. And so we had to somehow break the symmetry and bring in together the 2 halves of this molecule. Regardless, we thought that we could prepare this from a common precursor, which is shown here, this particular pyridine triflate. And we chose this particular pyridine triflate because we could prepare it in short order from these 2 precursors. And so that preparation is based on work from Data Schumann's group, but this reminds me to mention that there have been 2 other syntheses of complandin A, a beautiful utility of 2+2+2 cyclotrimerization by Dionisio Siegel's group at UT Austin, and recently Sukano has a beautiful synthesis of complandin A as well. But as I mentioned, our first order of business was to prepare this material from these 2 that was based on work from Data Schumann's laboratory. And so starting from these 2 precursors, we simply expose those to perchloric acid and dioxane and heat to 105 degrees. And in a single step, we can get a 65% yield of this tetracycle. And we can carry this out on multi-gram quantities. And so what we believe to be happening is that this enamide hydrolyzes to afford this ketoamide. And this ketoamide presumably has a high enolic content, perhaps by virtue of an intramolecular hydrogen bond. And that then reacts with this alpha-beta unsaturated imine, more than likely the iminium ion form, which then suffers a conjugate addition to afford this adduct. This then undergoes a monic cyclization to afford this material, and then a cycle dehydration then leads to the formation of this tetracycle in a single pot reaction. And so with this in hand, we can then first protect the secondary amine as the carbamate, and then we can carry out a dehydrogenation of this heterocycle to afford the pyridone, and then carry out a standard triflation to afford in 4 steps from these 2 precursors one portion of this molecule where we now have functionalization at the 2 position of the pyridine, if you will. So clearly, the challenge that remains then is to functionalize at the 3 position of the other pyridine and bring these 2 together. And so the way in which we decided to proceed was to essentially split our material in half and take half the material and hold it for a final coupling, and take the other half of the material and remove this triflate group. Now, our idea was that we would like to be able to site selectively functionalize at this position to introduce the other arm that we need for the coupling. And we'd like to do that using a CH functionalization method. And if we looked at a lot of the CH functionalizations, and Professor Jin-Kwon Yu did a wonderful job telling us about all the developments in his laboratory, a lot of these CH functionalization methods have relied on having a proximal functional group, or maybe not so proximal in the case of Professor Yu, that can site selectively direct metallation to a particular position. But we've worked very hard here to remove any hope of having some direction in terms of our approach to that pyridine. But what we were aware of is that the inherent electronics, as well as the site accessibility of this pyridine, could, in essence, enable us to site selectively functionalize here if we used the beautiful and powerful chemistry that Professor Scott told us about, which is really pioneered by the laboratories of Mitch Smith and Rob Maleshka, and also really popularized by the Hartwig and Miura groups, which enables us to achieve this borylation reaction site selectively to afford this boronic ester. And in fact, the conditions that we use here from my colleague, Professor Hartwig's laboratory, and we've worked closely with his group in terms of trying to optimize these reactions. And so it's very interesting to hear from Professor Scott that these reactions might have some reversibility. But in any case, we can take this material now, where we have functionalization of the 3 position and the material with functionalization of the 2 position, and carry out a cross-coupling reaction to now afford this pseudo-symmetric dimer, and simply removing the Bach groups then leads us to a synthesis of complandin A in 8 steps from the precursors that I showed. Now, what has been particularly nice is that this material has enabled us then to prepare other natural products in this family, which have functionalization at that particular position. And we're currently working toward the synthesis of other molecules in the complandin family, such as complandin B. But I wanted to finish up with a return to complandin B, which is shown here. And you will notice that the difference between complandin A and complandin B is that complandin B contains this additional carbonyl group. And so perhaps in nature it's the P450 cyclooxygenase that affects then oxygenation. And if that's the case, then it's surprising that one also doesn't see oxygenation here, but perhaps it's an enzyme that's specific. And so there are lots of questions about the biogenesis of complandin B that we wanted to ask. And so we simply took complandin A, albeit in the Bach-protected form, and subjected it to these sort of modified Riley oxidation type conditions. And what we find is that oxygenation occurs to give us this isomer of complandin B and not complandin B. Right, and that we can start to understand if we think about the mechanism for this type of oxygenation, where the selenium first has to interact with the nitrogen of the pyridine. And clearly, this nitrogen here is more accessible than that nitrogen by virtue of the fact that this nitrogen is not flanked by two groups, whereas here we're flanked by two groups. And so the challenge then becomes, how do we reverse this inherent selectivity that we have for oxygenation in order to access complandin B? And so returning to what we learned about these methoxyarines and methoxypyridines in particular, what we find is that if we have a methoxy group installed here, now notice that both of these pyridines are now flanked by groups at the 2 and the 6 position, we get preferential oxygenation here, which I believe supports this idea that the methoxy group mitigates the basicity and also leads to an encumbrance of accessibility to that pyridine nitrogen. And so we're only beginning to learn about the importance of these methoxy groups on these heterocycles. All right, so that's the story that I wanted to share with you today. And as I mentioned at the very onset, my group is interested in really putting ourselves in a position where we can arrive at interesting problems in chemical synthesis and try to identify reactions, strategies, and methods that would enable us to address these problems. But I wanted to leave you with a few conclusions that hopefully we've been able to articulate in this talk. The first of which is that I sincerely believe that in the modern day of chemical synthesis, especially with natural product synthesis, we're really striving for efficiency. And part of this efficiency might not only lie in the types of reactions that we use to obtain high yields and high selectivity, but in also trying to address families of molecules from a common precursor. Because once you invest the time and the effort to prepare a common precursor, and if you're able to parlay that easily into other molecules, that gives you an overall efficiency in building many different structures. I will return to this idea, as I mentioned throughout, that if one is able to achieve this carbon sp3 nitrogen bond formation, that will really change the way in which we think about alkaloid synthesis, because there are no methods outside of the Huffman-Leffler-Freytag reaction and the sort of specific dianion oxidation chemistry that I showed here for taking CH bonds, which and joining them with nitrogens, which have two alkyl groups on them. Okay, so there's lots of beautiful chemistry by people like Dubois and Christina Wine and so forth. But in all those cases, the nitrogen is always attached to an electron withdrawing group. Okay, but if you can have them attached to two alkyl groups and achieve the CN bond formation, that I believe will change the way we think about alkaloid synthesis. And then lastly, this idea of using cycloisomerization chemistry and CH functionalization, I believe, will continue to redefine the way in which we think about chemical synthesis. And so what remains for me to do is to thank the people that have done the work in my lab. I'm really indebted to a really talented group of postdocs, graduate students, and undergraduates. I try to highlight the names of people as I went throughout today that have done the work. Without them, none of this would be possible. A lot of this are ideas that really come from our conversations, and I'm indebted to a group that is very passionate about chemistry and also have fun doing chemistry. And so I hope that I'll have other opportunities to tell you about a lot of the work that I wasn't able to share with you today from other members of the group. And I'm also indebted, obviously, to the organizations that have funded our research and those that have supported us. We love Aldrich, and we've worked very closely with Aldrich and other companies that have supported us in terms of providing small amounts of material to do some of this chemistry. I wanted to finish up again by thanking and congratulating Scott for the invitation and to the DOC committee for concurring with his decision to invite me. I have to admit that I was really nervous when I came here to share with you our work because I've known Scott for a few years, and every time that I see him, he talks about my sister. Okay, my sister's a chemist as well, and he mentions what an impressive chemist she is, and so I really think that secretly he only invited me here to appease my sister. And so I felt very nervous that I had to live up to the expectations that he had of our family. And so, Scott, I hope that I'm at least a tenth of the way there. All right. But thank you very much, and I'll be happy to answer any questions.
All right, do we have any questions?
Lots of people have to catch a plane, I guess.
Over there?
Hi, Stephen Furley from City University, New York. Well, that was a great talk. I had a really hard time writing down all the structures, but with the kind of the failed Hoffman-Freytag but wonderfully inventive dilithium solution to forming that carbon-nitrogen bond, we obviously saw that great talk this week from Professor Yu, and you had a pyridine and a benzylic position, and at some level it would be perhaps easy to imagine, although perhaps difficult to realize, a way of using a coordinated activation of that particular pyridine benzylic position and have the reaction almost running in the opposite direction, where you're starting off at that end rather than at the nitrogen end. Did you try anything like that with organometallic activation in that position and an oxidation kind of
Absolutely.
scenario?
So, the initial intent was to actually think of that pyridine benzylic position as one X-type ligand if we had it deprotonated, and the nitrogen amide as another X-type ligand. And so if you could bring it together with a metal and effect a reductive elimination, that would enable you to form that bond. Now, granted, it depends on the sort of, you need a square planar geometry for that reductive elimination. So what was unclear to us whether palladium would be the best metal for that, or perhaps we can think about this from an Ullmann coupling type standpoint, so copper or other iron or other types of metals for CN bond formation. And so we actually started that chemistry by making a dianion, treating it with palladium-2, and see if we get a reductive elimination. We tried copper, we tried iron, we tried a whole range of metals. And then we started to think that perhaps in order to achieve a reductive elimination, what we might have to do, a la the work that Professor Yu told us about, is oxidize that palladium from palladium-2 up to palladium-4. And then perhaps that would facilitate the reductive elimination. So we started to add oxidants like iodine and other oxidants. And the chemistry worked beautifully. We got excited. And then we ran the control experiment where we left out the palladium and we simply added the iodine, and it worked even better.
Okay.
Okay.
Thanks very much.
All right, do we have any up there?
Yeah, Daniel Cohen from Northwestern. I have two questions. The first is for lycopodium A. Did you try any of that work that Hartwig developed using a Lewis acid to block the pyridine, so that nitrogen, where he shows you can coordinate a Lewis acid to the nitrogen of a heterocycle, and then you can do coupling so that the more accessible pyridine would be blocked by a Lewis acid, and then you can use selenium to selectively oxidize that other position.
Absolutely. And so that's actually where we started, right? Because we wanted to do this using dative blocking groups, if you will. right? And so we looked at a range of Lewis acids, boron, aluminum, you name it. We looked at all of that. We also then caved in and looked at, covalent linkages like N oxides and so forth, right? We were not successful with the data sort of blocking strategy that you suggest, presumably because there's a pretty quick exchange, right? So even though it's interacting with that nitrogen, for example, boron, there's an exchange. And so in all those cases, we still see predominantly the product that results from the selenium engaging the more accessible, if you will, nitrogen. Presumably because we still have a pretty facile exchange, right, of that boron, if you will, or other Lewis acids with that pyridine. So the date of linkage is not as robust as we would have hoped. So we absolutely looked at that. That was what we looked at first.
And now one last thing. For that carbon-nitrogen bond formation, do you think possibly with iodine it may go through an E1 mechanism? So sulfur, you showed that there's inversion over there, but that's sulfur and that doesn't leave as quick as
Absolutely. So with the iodine, in fact, we suspect that it's more of an electron transfer mechanism, and that's been shown. So going back all the way to Don Cram's work on conductive Tor mechanism and the ways in which you think about, electrophilic substitution mechanisms, is that, you bring this large electrophile close to this sterically encumbered anion, and they can't quite get there. It's like the frustrated sort of pair, and then you get an electron transfer, and it's actually that leads to the bond formation. And that's also been shown by people like Bob Gawley, that you can actually have a change in mechanism as you go from methyl chloride to methyl iodide in terms of electrophiles added to sterically encumbered dianions. So I think that electron transfer actually might be at play there.
Thank you.
A couple of questions. One is a follow-up to the one over here. You already have a solution to that Hoffman-Leffler-Freitag reaction, but thinking back to Professor Yu's talk, if you were to trap carbon dioxide on the basic amine, you would end up with a carboxylate. And I seem to remember that he had cases where this carboxylate was activating to a remote, I don't know if it was SP2 or SP3, but could you form an intermediate that just had carbon dioxide there that would allow
Absolutely. And so these are all wonderful suggestions because ultimately we solved it, but we solved it with fairly brutal conditions, right? I mean, butyl lithium is not functional group tolerant, right? And so ultimately we would love to have organic transition metal ways of doing this. Now, the suggestion that you have there, it's a reasonable one. We haven't necessarily looked at making what you're suggesting, which would be a carbamate of sorts with a carboxylate, which then could in principle direct the palidation to that pseudobenzoic position. We haven't looked at that at all. So I think that these possibilities exist. For that particular substrate, though, we take the sort of Occam's razor approach, right? That the simplest way for that particular substrate is a dianion with iodine, and it gets the job done. But in terms of moving forward, these ideas that you're suggesting are very good ones. We had a recent paper in Angewandte where, in fact, we can now start to look at zinc as a way to template things to do this sort of oxidative CN bond formation. So I think that in terms of organic transition metal ways to make the CN bonds, that's simply just only starting to emerge, and I think that there are many possibilities. Yeah.
One last thing, I was excited to see you were talking about at the beginning of the talk. You mentioned biomimetic synthesis, and I thought, plants have figured this all out, and they must laugh at us puny humans, with our brutal conditions. But looking at in a case like you were doing the cycloaddition onto the oxidized metapi area.
Yeah.
How does the plant do that? Is it a concerted, a pericyclic reaction?
In that particular case? Well,
yeah, I mean, how is the plant assembling that particular?
That particular compound. So that actually arises from a terpene biosynthesis. So it's again through a polyene cascade, and then you have sort of a Wagner-Muirwine shift to go to the 3-2-1 bicycle. So it's a very different way in which the plant puts that together. And again, as I mentioned, unfortunately, they're fantastic processes, but the yields for some of those processes are pretty low if we're going to go about doing it the same way that the plant makes those particular compounds. Hence the sort of laboratory approaches that we're looking at in that particular case. But I would contend that not only plants laugh at us, I'm pretty sure that a large number of other scientists laugh at us as well in terms of the futility in which we still can't get the levels of efficiency in putting some of these molecules together.
Jason Birch, Genentech. I wonder if you can comment on the importance of the tertiary center via sort of a Thorpe-Gold effect on your indene cycle addition, and if the answer to that is it's not that important, is there any hope of doing that intermolecularly at some point?
Yeah, that's a good question. For sure, we've done compounds where we don't have that gem dimethyl group there, and we can still get that cyclization. Certainly, the Thorpe-Gold effect is somewhat important because in those cases, they are slower reactions. We've only looked at those qualitatively, but they are slower. And so certainly that's important, but it doesn't completely prevent the reaction from happening. The challenge with the intermolecular cases is that you start to get head to tail dimerization of the alkyne groups in addition to the chemistry that you're looking for. And so if you have an alkyne partner where you can sacrifice a lot of it, then you can, in principle, do it intermolecularly. But we've sort of restricted our studies to the intramolecular version because we do have this competing head-to-tail dimerization to make enines that competes with that process. Yeah.
Up there?
Svetlana Kulik, Temple University. I noticed that in your platinum catalyzed cycloisomerization, you had one of the examples where you had cyclopropyl acetylene derivative.
Yes.
Were you intending to initiate an additional cyclization event, or was that just to demonstrate the usual?
Right. It's a good question. So clearly, we looked at a whole range of commercially available acetylenes for that chemistry. But if you were thinking of sort of the Newcomb type ring expansion then from the other cyclopropane, we don't see that in that particular case. But I will say that, perhaps if we had additional substituents on that cyclopropane, like the Newcomb sort of radical clock cyclopropanes, we might start to see other rearrangements. But for our particular chemistry, we don't see that.
So have you tried? Was that the intention?
No, that was not the intention for that particular chemistry. It was just to illustrate that it would survive, actually, processes where one might expect to see sort of strain release ring expansions. Yeah.
Right, any further questions? All right, we have one last order of business before we thank Richmond and all the speakers, and that is for Scott Seaworth to close the current meeting. Okay.
Yes, I just want you to indulge me for another minute or two. And I'll invoke, thinking maybe I should invoke my PhD heritage there, and I just say just another minute. This has been I'll say it, this has been a great meeting. I've gotten a lot of thank yous and acknowledgments from everybody up here on stage, but frankly, it's pretty simple to put together a meeting that's this awesome. All you do is invite the right people, and that takes care of the quality of the meeting. And then all you have to do is deal with the 300,000 details that hopefully nobody really has to notice. So it was a great honor for me to be able to do this. I'm very thankful to the Division of Organic Chemistry, which makes this all possible. They're the ones that not only underwrite this and make it happen, but and trusted in me. I went to them with a plan, and they basically said, we're not going to micromanage this, just take care of it yourself. And so I did. So I'm very thankful to them, And I hope that if you're not already a member, I'll echo what Marissa said, that it's a great piece of the American Chemical Society, and it's worth being a member. I'm also very thankful to the University of Washington for providing these outstanding facilities. So I'm very thankful also to all of the people who agreed to come and made it easy for me to assemble this group of speakers and even rearrange them at the last minute so that we could make it possible for Jack Roberts to see the Dave Evans talk on Monday night instead of Tuesday, where it's always been since the first one here in 1959. So very thankful to all of them. I'm thankful to all of the people here on campus, as well as Marissa, who have helped me put this together and take care of those 300,000 details. Paul Hopkins, who not only is the chair and facilitator here at the University of Washington, but if somebody I met when I showed up for graduate school at the same time in 1977, which doesn't sound that long ago to me, but okay. So, of course, we have lots of sponsors and exhibitors that also contributed both to the poster sessions, a little bit of extra entertainment out there, and also helped underwrite the costs of running this meeting. I'm going to particularly highlight three of them. Theme, Chemistry, and Wiley for, well, Wiley is intimately involved in this meeting and essentially always has been, but for providing, these two for providing the prizes for the poster awards that we've been giving out every day. Organic Letters for a very significant level of support, but also, and Renee John for all of her efforts in organizing the 5K fun run, which was extraordinarily successful this year. We had, I think, 3 times as many runners as we did in 2011. And so that was just amazing. The session chairs, who graciously agreed to come and participate so well and make all of those introductions so eloquent. And so I'd like to and you can see a number of these names appear on many of these slides. So major contributors there. The volunteers from the University of Washington and Temple University, could you stand up? I tried to, if any of them are still here. They may have been forced back to left. Thank you. Thank you. What else? Okay, so this is just a small portion of the executive committee that we get to always go to the American Chemical Society meetings and spend all afternoon on Sunday in a small closed room with 30 people discussing all sorts of minutia. But I'm going to reiterate my thanks to Brian Meyer, because not only does he run the website for the division, he's hosted through that the website for this meeting and archived many of these websites, and this one will be archived as well. Brian and I worked together for the last, I'd say, at least a year, maybe 2 years working on this, and sometimes on an hour-to-hour basis to get this stuff uploaded, and he was extremely responsive. There are some changes to this list, so I'm going to cross out the executive officer and pass the baton to Marissa, and with great best wishes and all the help that I'm able to have. And the list goes on. This hall, with this beautiful facility. So Rita Calabro is the one who keeps it beautiful and made so much of this easy to do. And the University of Washington Conference Management Group, in particular, the two lovely ladies who've been sitting out there at the table and coordinating all of the bus details and loading and arrangements and adjusting food and counting the number of bottles of beer at the end of every morning, so we could just try to keep it running on track. And finally, thank you for coming, because if you don't show up, the meeting doesn't happen. And I'll see you, I hope, in Maryland. So with that, we'll close. Thank you again. Oh, and actually, one last thing, you know, there's always, God, who else am I forgetting? So we were very fortunate to connect up with Puget Sound Video, who have done a spectacular job of doing the AV, just amazingly good job, and providing those spectacular videos you see out there. So I look forward to being able to help share those with you, members of the Organic Division. So let's give them a round of applause as well.